Okay, so my name is Magda Jankowska, and with Jacek, we'll be presenting this talk, Machine Learning and its Use Cases for Visual Analysis. I will start with general information about machine learning, and Jacek will follow with real-life problems and solutions, basically ones that we are facing at Dash Hudson. So I will start with placing machine learning and like how it relates to other buzzwords as artificial intelligence and deep learning. So first, artificial intelligence is a very broad and a bit vague definition. It's a term that Andrew Moore defined as a science and engineering of making computers behave in ways that until recently we thought required human intelligence. So as you see, this is a quite a broad, a bit inspirational, and a kind of moving target as well definition. Machine learning is very well defined. It can have very mathematical definition, and it's a subset of artificial intelligence. There are AI systems that are not machine learning systems, but machine learning are the most successful and popular systems. So machine learning is, according to Tom Mitchell, big guy in the area, is the study of computer algorithms that improve automatically through experience. So we have computer programs that perform tasks without being explicitly told how to. And this experience comes in the form of data, and we call it training data, data from which a program learns how to perform the task. And you can define it very mathematically with some measures of performance saying that we can actually improve that using this training data. And in recent years, a term that became very popular is deep learning. And deep learning is a subset of machine learning in turn. It's machine learning with a type of algorithms which are artificial neural networks with many hidden layers. And this type of algorithms and this type of machine learning became extremely successful in many, especially complex problems. And we will talk a bit about this later. So when we talk about the machine learning, we usually divide it into four types according to what kind of supervision, of human supervision, is required. And this is not talking yet about how, whether we use deep learning or artificial intelligence or different methods. It's about general about the problems and types of learning. And this is usually divided into those four: supervised learning, unsupervised one, semi-supervised, and then reinforcement learning. And for supervised learning, what we want is, for a given object, our input, we want to output some answer. And it is supervised learning when we have training data with already known answers. So we have this human supervision, or this kind of a teacher that shows us examples of objects and the answers. Well, in unsupervised learning, we just have the data, no labels, no answers are given in the training data. Semi-supervised, in between those two, we have some data with the labels, with those examples of answers, but we also have a lot of data that doesn't have it. And the question is, can we use this unlabeled data? And reinforcement learning is a totally different kind of learning, in which the way our software learns, we usually call it an agent then, is by observing the environment, making some actions, and obtaining rewards or punishment. And based on that, the program learns the good policy, which actions to select. So I will now go through those types and give concrete examples to focus our attention. So there are two main types of problems for supervised learning, and that's regression and classification. In regression, our answer, what we want to output for a given input is a number, is some numerical value. And this is supervised learning, which means that we have this training data with the examples of the real answers, real values. And the example problem that Jacek later will be talking about is a problem that we face in Dash Hudson. When we want for a given image, we want to output a predicted value of how well it will perform on the when published on Instagram with some measure of performance. So there is some numerical value that we want to output. And our training data, in this case, there are actually images that already were published that we know the value, and that's what we learn from. So we have this training data, on that we train our predictor of the image performance. Another, as I said, the other important problem for supervised learning is classification. It's kind of similar, but the answer is not a number. It's a label out of a finite set of labels. Again, real life example here. Let's say for a text, we want to output one of two labels, with text or without text. So we want to recognize whether the image has text or not. So the outputs are labels true, false. And again, supervised learning, we have training data with already known labels. So we have some images with the label with text, some images without text, and based on that, we train our classifier that predicts that. I just want to make a note here that basically all those examples that I give have images, because that's what we'll be talking about as our objects. But of course, the objects do not have to be images. They can be any kind of objects that we want, that we are interested in, right? There can be text documents, records encoding buildings, records encoding people, whatever data we have. So that was supervised learning. Unsupervised learning, we want to learn some patterns in the data, but we do not have any labels given to us, any ground truth that we can trust. And the by far most important problem in unsupervised learning is clustering. And this is the problem of, given a set of objects, divide them into sets so that similar objects end up in the same group, the same set, cluster, and similar ones will end up in different clusters. Again, real life example, we want to find segments in the images that are posted on a given Instagram account. Again, this is unsupervised. We are not given some labels. We are not given labels, flowers and buildings. We want the program to find those groups and then discover, gain insight, what kind of groups are they in this given set. Now, semi-supervised, as I said, lies between those two. The problems are usually the ones that we have for supervised learning, like classification. The whole question is, we also have some data that is unlabeled, that nobody told us the answer for. Can we leverage this data? And the answer is that there are ways of leveraging this unlabeled data to improve our performance. And that's what semi-supervised learning is. Reinforcement learning is a totally different beast. And the example that I want to give is something that I myself find mind-blowing. Chess player, from Google's DeepMind, AlphaZero. It plays chess, Go, and I think it's called Japanese chess. I don't know, this shogi game. This program actually had only encoded the rules of the game, let's say chess, and then it played thousands and thousands of games against itself and received those punishments and awards for winning and losing. And that's how the policy was learned. And the kind of paradigm shifting in this case is that it's not only that it's better than previous programs, but it actually discovered some totally new strategies for playing chess that people never considered, and now they study them. So we were talking about the type of problems, and now let's talk a bit about how we can do this. So what are the methods that allow programs, the software, to learn from the data in those different types of problems? And recently, a very successful types of data types of algorithms that are used are artificial neural networks, and that kind of divided the methods into artificial neural networks and the other, or let's call them traditional methods. So the traditional methods, I call them traditional, they are not neural network based. I listed on this slide 3 for each of those regression, classification, clustering problems. And I want to make 2 points about them. One is they are not obsolete. They are still very useful, especially for problems that are not so complicated or do not have data that is very, that have data that is structured and doesn't have a lot of raw features. Those methods are still very good. Also, they can be used, as we will see in part of the Jacek presentation, after some pre-processing using neural networks or the deep neural networks. This is one point. And the other point I want to make, that if you're using Python, then the place to go, in my opinion, but I am not alone, is scikit-learn. It's a, in my opinion, great Python library that allows you to choose and train and apply those machine learning methods and evaluate them. So at the end of the presentation, there is a slide with the selected resources, and it is listed there as well. So those are non-artificial intelligence methods. So what is artificial neural networks methods? Artificial neural networks are not new at all. The first one, I think, was proposed in 40s, and it was inspired by neurons in our brains. So as neurons in our brains are interconnected, and a neuron sends signal, receives electrical signals and sends signals to connected neurons. Similarly, in the artificial network, on the right side, we can see an example of a simple artificial neural network. We have an input, so we encode some this object of ours and send this input to the network, and then each neuron sends the values, output of the neuron, to the next layer. A neuron calculates some mathematical, performs some mathematical calculations on those inputs and sends output to the next layer. So at the end, we have output layer and we get our answer from that. So for example, we can see here how we could use it for regression. We want some number. So we encode our input, push it to the network. In between, those magic happens, this mathematical calculations happens. At the end, we are getting the number for the regression. Of course, the whole big question is how we train this network so that it actually does something that we would like it to do. So while the artificial neural networks are not new, they recently have this big renewal in interest, and those new networks are ones that are deep, which means they have a lot of hidden layers. They have the whole structure in between the input layer and output layer. And they became extremely successful in many problems, and especially in problems that are complex, and especially for problems that have data that is raw, that is unstructured, such as images, sound, raw text. And there are many reasons why it actually, after so many decades since the first neural networks was proposed, why they are now so successful. And some of them is that we now discovered, people discovered better training algorithms. There is much better processing power, which allows us to train those big networks, and there is increased data availability. And those neural networks, the big ones, require a lot of data to train them. So these are the general informations, and I will pass now the microphone to Jacek, who will illustrate those on the problems that, that we are facing at our company, Hudson.
Okay, thank you, Magda. So first, like Hudson deals with a lot of images and visual, basically visual assets. Can you go to the next slide, Magda? With the birds, yes. So, and the problem is that if you look at those images, for you guys, we can say, okay, those are the same images, just one is smaller than the other. But if you look at the raw data, or like raw bytes, behind them, they're actually completely different beasts. Like they can be encoded differently, they can have slightly different crop, which means that all the pixels going to be shifted. And if we have some very rigid method of dealing with them, then any small change will actually change the output drastically. So, so that's essentially the general problem that image recognition needs to deal with. And actually, it turned out that the deep neural networks is actually the right tool to do that. So, if you can go to the next slide. Yeah. So, what those deep neural networks are typically consisting of is what's called the convolutional layers. So in this case, on the left-hand side, we have the original image, which has 3 layers typically. So that's red, green, and blue. Okay, so we have all the color information on it. And in this case, we have an image that's like 10 by 10 pixels or something like that, like that. Yeah. And at each step in that network, which is just a bunch of hidden layers, we have those convolutional kernels that essentially look at a very small area of the image at once. In this case, it's basically 3 by 3 pixels, and they basically produce 1 pixel, which is basically which essentially aggregates information from that 3 by 3 area and all those 3 colors. Okay, and then we stack more of those layers on top of each other, just to preserve the same amount of information, because in this case we have started with let's say 10 by 10 by 3. In the second layer we have 10 by 10 by 1, which means that we lost a third of the information, so we can stack more layers to actually retain that information, technically speaking. Yeah. So if you go to the next slide. So those deep neural networks, they tend to get super complex recently, because we just basically realized. So at first, like the problem with regular neural networks, they had typically 2 or 3 hidden layers, and that's it. And the problem was that the more hidden layers that people try to throw into them, the worse results they were getting, because that essentially makes so that you have vastly larger number of degrees of freedom of that system, meaning that to train this properly, you have to have significantly more data. Okay? And we didn't have that in the past. So AlexNet is the first network that actually dealt with that basically problem in a deep sense, and was by Alex Krzyzewski. And this network is like 6-7 years old. So it's just that, and it like literally only consists of 7 layers pretty much, and each of those layers. So on the left we start with 220 by 220 by 3 image. So this is your basically regular image that's basically scaled to a square and basically 3 layers deep for each color. And then at each step we gradually decrease the image size in pixels. So the first so in the first transition we're going down from 224 by 224 to 50 by 50, but in order to retain that original information, we are adding those extra layers. So in this case, in case of AlexNet, they just went up from 3 layers in the input, which is the RGB channels, into 96 different random at first layers in the second in this basically in the second stage, and each of those pixels on that image was only looking at 11 by 11 area in that original image. Now actually we know that if you go even smaller than that, if you only look at 3 by 3, 5 by 5, and you only reduce the size of the image gradually by a few pixels each time, and just adding 1 or maybe 2 layers max to basically to the depth of the image is actually better. But then this needs more and more layers, and and we wouldn't be able to even see that entire image on that slide. So this technically works on image. Can you go back, Krista?
Sorry.
This technique works like basically like the pasta machine. When we have thick slab of dough, and then we pass it through the pasta machine, making it thinner and thinner and thinner. However, we just basically change the pixel size gradually from the original image to, in this case, for basically for Alex, it was 13 by 13. So we ended up with 13 by 13 pixels on the image, but not 3 layers deep, but 256 layers deep. And then it goes, and then basically those features are extracted into those dense layers, and that's where just the traditional artificial neural network things happen. Or we can actually take those layers and you can apply it to any other traditional basically methodology, and that's also what we do as well. So in the next slide, this is for example the Inception V2 network that was just developed a few years after AlexNet, and we actually also keep using it to this day because it just performs very well, and it's still like pretty compact network. It only has 27 hidden layers only. It means that every number in the input has to go through 27 different basically mathematical operations and mixing and shuffling until we get to the solution at the end, which is whatever the goal for this is. So in case of AlexNet was 1,000 output layer, which was 1,000 labels that they were trying to predict. Like in case of Inception, it's also a couple thousand labels that they are basically trying to predict what's on the image. Okay. And the good thing about those networks and the good thing about the software that's being developed by Google to basically facilitate that and to compute that, which is TensorFlow, that's all open source in the sense that everybody can use it free of charge, free of any royalties, licensing, and basically whatnot, meaning that even if you don't have the power to basically create those networks, and the deeper those networks get, the crazier they get, like in terms of the requirements and basically both the compute requirements and the data requirements. But because they are publicly available models, everybody can just download and use it. Okay. Yeah. So our first kind of task that we do is basically predict the engagement of Instagram photos, and so Magda already explained how this problem works in general. So this is essentially a regression problem, or in this case, if you, for example, want to just add a label, is it good? Is it like star image or a bad image? We can call it a classification problem. It's either or, doesn't really matter that much. And what is important is if you try to model it for all the brands at once, and that's what typically players like Facebook, Google, Instagram, Pinterest do, then you are not very specific to a particular account. And the cool thing that we are doing is we only build your prediction based on your data, okay? And that allows us, first of all, we are dealing with much smaller models, and those models, because they are focused on your data, they actually perform better than any model that we've tested that is built on like let's say everything or everything from that industry for that matter. And also this allows us to rebuild the model on regular basis. So your models for your brands are constantly being updated in our case on weekly basis. So if you added a few photos and some trends change, we can notice that and we can adjust your predictions accordingly. Next slide. Yeah, so so basically in general, how we do it is basically we grabbed basically all the photos that are the account media, which is essentially all the media that that brand posted, which can be a couple thousand, and it's typically a couple thousand photos. And then we build a model based on that. And we also have basically a collection of photos from all the accounts that we know about. And then we build another model that's basically kind of like a global, see what's good and what's bad photo in general. And we just basically combine those two for your account specific model. Okay. So another application that's actually deep neural networks are actually very useful for, and that's also brings it back to the thing that we are basically squeezing that image through that smaller and smaller die into basically into this feature vector, is that when we end up with that feature vector at basically at the end of the line, it looks more like a traditional data format in terms of like it's not basically 3-layer deep and like 1000 by 2000 pixels. Is essentially, let's say, 2000 numbers, and that's pretty much it. We can use it for search, and we actually take that basically output vector, which are called embeddings. And if you've dealt with those like basically in those programs, basically the word embedding will be actually coming up very often, and that's the layer just right before the end of the network, when before we apply it to a specific problem, we have this embedding layer, which is like, let's say in this case, in case of inception, is 2000 vectors long. Currently with Keras and TensorFlow, you can actually adjust it if you want it. And then we apply several procedures that are more traditional, like in this case, matrix factorization, to basically reduce that large space into a feasible amount of features that we can deal with, that we can feed, in this case, to Elasticsearch, that we can use for searching. So we essentially can convert any image into this search representation and be able to use a general purpose indexing like Elasticsearch to actually apply it. And without even thinking, like, what do those features basically represent? If it works on text, it will work on images as well. Okay, next. Another application, that's something that Magda touched on while talking about clustering, is segments. And in segments, we essentially apply hierarchical clustering to basically group content of a particular brand into manageable pieces that should have similar looking photos to them. Okay, so this is the actual example of how it looks on the platform. We give you segments for your own brand if you want to, but you typically know your content, so you don't need that. But what's very popular is essentially applying that segmentation on all the competitive brands, because you may not be a content creator there, you may not be the content manager, you will not be. So this allows you to quickly glance what other brands have as basically as their content, and how it performs, and what kind of groups they have. And in case of clusters, we can make them highly customizable. So if you look above those basically visual examples, there is basically a slider to select less and more clusters. You can change how many days we take the data for. Like, you want to see the more like recent ones, you can change from 3 months to let's say 1 week or 1 month, and also sort them differently. So you can just browse that content in a much more manageable way. Okay, next one. So yeah, so in terms of like basically in terms of like resources, you can choose yourself and basically try to learn it. There's basically Scikit that Magda was basically mentioning. There is also Keras, and there's TensorFlow. Now TensorFlow is now linked with Keras, but yeah, basically Keras is basically our two libraries you can use to actually apply deep learning models, not just for images but for everything really. But they have a huge library of building models you can use to essentially process images and basically play with it and see what you get. There's also PyTorch, which is another Python-based neural network toolkit. And if you want, there is also a book by Aurelie Media, which is a very good publisher about scikit-learn, Keras, and TensorFlow. Although I have to warn, like, these things, they change quite often recently, and the development in this area is quite significant. Meaning that if you take a book from 2-3 years ago, it's probably already obsolete. So the best place to learn is probably from the documentation on each of those like packages, and from the examples you can find on the web. Okay. Next. So, like, if we look at Dash Hudson, so what Dash Hudson in generally does, Dash Hudson is a visual marketing software for the world's most important brands. And if we read basically closer, it's built for discerning, create, measure, predict, and publish photos and videos, see trends, analyze, and enhance performance. So all of this, that's actually part of all the solutions that we've showed, is essentially, that's all this basically measuring and analyzing and enhancing. That's all the smart stuff that can be done with deep neural networks. And if you guys want to join us, we have currently actually open positions at our product team. We have an open position for a DevOps engineer, for a full stack developer, and for a senior full stack developer. So yeah, so that's it. And next slide. Yeah, so thank you very much. So it was me, Jacek, and also Magda. And you guys, if you have any questions, feel free to jump in, and we'll be here for you to answer them.
All right, feel free. I had one question, but for others, so I'll ask mine first. For the others, feel free to unmute yourself to ask questions. So to keep up to date with the latest like technologies and libraries, you mentioned that the best source is to go read the documentation for TensorFlow and these other libraries. But how do you actually find out about the libraries? Like that requires you to be aware that those libraries exist, that you want to use it for that, to read their documentation. You must have to review some sort of like umbrella articles or materials to find out about the libraries. How do you find out about that?
Well, I myself cannot give an cannot give an exact source. I would say when you are in the area, you tend to well, listen and hear about those different sources, and yeah, I cannot come up with one blog or one source that you would come up, but when you kind of follow the area, you would definitely pick up those important ones at least. Yeah, Jacek mentioned this book. I will say it is maybe obsolete because it's 2 years. I like it. I like it because it gives you the kind of like big picture. Like whenever you need details, I go to the. Of course, I don't get all the details from any book, but it gives you kind of overview of what's possible, and yeah, and it also lists those the solutions, the libraries that we like. Maybe Jacek has something to add, but that would be my answer.
I actually lost a little bit of the.
You lost the question?
Yeah, I definitely lost you guys, so I didn't hear the question.
Okay, I'll just, so you mentioned that the best source of information in terms of read upon was the library's documentation, but that requires you to be aware of the libraries. Like if you're going to go do a deep dive on the TensorFlow documentation, and because you know that's going to suit a certain business need, you had to have been first aware of TensorFlow. So how do you become aware of the existence of these, as you have these business drivers for a company, how do you become aware of these libraries that would meet your needs?
So thankfully, there is only a few of them really. There is TensorFlow, there is PyTorch, there is there's like maybe 2 or 3 more, and that's pretty much it. We are using TensorFlow, which is the kind of this basically kind of the de facto basically standard of doing it that everybody can use, and so that's basically what I'm what I was basically saying, that it's not that difficult to just basically jump in, try to find some basic examples, basic tutorials, how it's done and how it feels like. And yeah, I don't think there is a problem in terms of like finding different solutions, because there's only just a few of them.
Can I add a few things to that? I think we are lucky that we had those popular ones right now. But I mean, like I was there totally lost, and I was doing master actually with Magda. We were in the same group, and Jacek as well. I think the thing is like you first need to know the basics of machine learning, like what Magda introduced, what are the main categories there, and the problem you need to solve. And when you have the problem, when you know like what kind of models can address that specific problem, then you can start searching the implementations for the models. And many of them nowadays happen to be implemented in those a few popular ones. But before those, we were also using Weka, like some older ones. But they all comes down to the same algorithms. It's just like a different, fancier implementations.
There's a question on the chat. I'll read it. There's a ResNet architecture. Wondering why you chose Inception over ResNet.
We actually we are using ResNet as well. We just basically showed Inception because it's manageable in size. Inception has like 30 layers, and it's like 4 years old. ResNet tends to have upwards of 200 layers, and it requires much more memory to manage it. And it is better, but not by a huge margin. The differences between those is literally a couple percent. And we do use actually ResNet and Inception right now for various different problems. And there are actually new networks that are that are popping out with TensorFlow 2.3. There is also EfficientNet, which kind of basically promises the same kind of performance that you can get from ResNet, even more in a network of the size of Inception or less. So we'll have to basically look and see. That's something that essentially changes. It's not that the frameworks change, is that those big companies, they basically develop those better networks, and when they kind of basically build tools on them, they basically make them public. And so it's not just being aware of the toolkits, it's more about being aware of the new networks that are popping up. And in most cases, you can just swap between one or the other, no problem, and basically solve your problem using something else. So ResNets were basically popular for a couple years, 2 or 3 years from basically now. Now there are new types of networks that are basically popping up, and you have to be vigilant and basically see what's around, what kind of benefits you are getting of like switching, because this is not often very simple to just switch your network. Yeah, but yes, so those things change, and they change quite quickly recently. So you would have to be very focused on that.
Any other questions from the group? Oh, there's another in the chat. Is Dash Hudson processing and predicting video now?
Yes, I can answer yes to the question. We are working on it, and we are working on the solution to actually do that as well. At the end of the day, we want for video and like for photo and video have no difference in terms of like stuff we can offer for those media, basically for those mediums. Obviously, video has one extra dimension, which is time, and it's not that straightforward to deal with. But we are working on the technology to cover that as well, and hopefully you'll be out at some point.
Mm-hmm. You mentioned in your answer that about time being one of the challenges in dealing with video. Is there any other challenges of videos compared to images? That the main one?
I mean, there is obviously one thing that we are missing in this picture, which is the audio basically part. So video is typically not just moving image; it's moving image with sound, while image is just basically fixed image with no time and no audio. Thankfully, on like basically for the brands that we are dealing with, typically what's in that video in terms of the audio stuff doesn't really that matter because it's all very visual. Like if you think about Instagram, Pinterest, Facebook, those like very quick contents, the audio is pretty much just a background music and that's it. It's not that important. If you'd want to analyze, let's say, movies or like longer forms of content, sometimes audio is more important. Like in this case, you can tune in to this basically Halifax event as a podcast and still have benefit from it without even seeing anything. So basically there is extra complexity with the audio part, but that's yet another problem.
And with the time that Jacek mentioned comes basically interconnection between the images. Video is something as a set of images, right? It is important how they are ordered and how they are connected. So we have to take that into account as well when processing each image, each frame from the video.